We present policy stitching, a method to learn transferable robot policies in different tasks. Suppose we train robot 1 in task 1 and robot 2 in task 2, and now we want robot 1 to perform task 2. If we directly transfer the trained policy, it doesn't work in the new environment. How to reuse the learned knowledge of the robot and the task in a new environment? We adopt a modular network that decouples robot and task-specific representation. The task state is the observation of the object and the goal position, while the joint state contains the angles of the robot joints. The robot module takes in the embedded states from the task module and the joint states and outputs the action. When doing policy stitching, we stitch the task module of one network to the robot module of another network to get the reassembled policy suitable for a new environment. However, the module's misalignment issue makes the stitched policy malfunction. We observe that modules interfaces trained in different environments have an isometric transformation relationship. In different networks, the embedded task states has rotation, reflection, rescaling, and translation relationship with each other. To tackle the misalignment issue, we transform the embedded task states to relative representations, which are approximately invariant in different networks. Then we can stitch the task module 1 with the robot module 2. Because the two modules have similar latent representations at the interface, the stitched policy has good performance on the target task. For the zero-shot transfer experiment in simulation, our method makes the robot successfully pushes the object to the goal in some cases. In comparison, the ablation method without relative representation can enable the robot to touch the object but rarely push it to the goal. And the planned MLP baseline makes the robot swing its arm in the air randomly and rarely touches the cube. For the few-shot transfer experiments in the simulation, our method achieves the highest training efficiency compared to other baselines. In real-world experiments, our method gets 40% of success rate, and the robot can always touch the object. In comparison, the ablation method cannot succeed, but the robot can often touch the object. And the planned MLP baseline never makes the robot touch the object. For the few-shot transfer in real world, we initialize with the stitched policy and fine-tune it in the simulation for about 2 hours. Then we fine-tune in the real world for about 5 hours. We get 90% of success rate with our method, 60% with the ablation method, and 55% with the MLP baseline. For modular interface analysis, we visualize modules interfaces of policies trained in different environments with PCA. The relative representation enforces an approximate invariance at the module interfaces. Without it, latent representations have an isometric transformation relationship. We also calculate the distances of module interfaces of policies trained in different environments. With relative representation, policies trained in different environments have more similar modules interfaces. The cosine and L2 distances between the latent representations at the interfaces are much smaller. For more details of our method, experiments, and analysis, please refer to our full paper. Thanks for watching.